Thank you, Jan. Thank you, Dominique, for inviting me. It's a real pleasure to be here and be given the honor to share with you some of the ideas that over the years I've been developing about accessibility, usability, user experience of user interfaces in general. So my goal today, the kind of ideas that I wanted to share with you is that in a sense, with the web accessibility, we are moving towards a plateau, a level of accessibility, usability, upon which is very difficult to move. And I think that this goes well beyond the technological aspects. So it's not dealing with the HTML or with PDF, with tagging, with other, ARIA, accessible, rich internet applications. Those kind of things help developers to produce a website or a web application or a mobile application that is accessible or usable up to a certain point. Because applications become more and more complex, because usage contexts are more and more varied, because of users' properties, characteristics, features are more and more varied, think of age, different age groups, and the kind of difficulties, or at least different ways in which they approach this kind of technology. All of this is going to make a very difficult world for anybody wanting to produce usable or high level of user interfaces with high level of user experience in any way that could be measured. For example, think of these kind of barriers that are very difficult, in my view, to overcome. These are barriers dealing with how people make sense of what they perceive in a screen, in an audio channel, whatever. Difficulties in understanding how to interact. What can be done at a certain point on a certain screen, why something doesn't behave as expected, information maybe being too complex, or interaction options being too complex compared to the kind of expertise, competence that the user is showing, maybe also abilities. Cognitive barriers, learning new procedures, comparing outcomes, performing complex and long tasks, coping again with information overload. All this is going to be very taxing, to be very demanding on people that for some reason, age for example, but maybe cognitive disabilities, maybe situational environments. I'm using a website or a kiosk to buy a e-ticket somewhere where I don't have time, I'm pressured by people behind me, etc., so I'm stressed. It is as if I were a cognitive disabled person. Think of older adults. A typical barrier that you can find there is that people of that age are afraid of using technology. They are afraid of using technology so that technology would break and would be unable then to do what they used to do. Think of a cellular phone and making calls. If one way of thinking is that if they use it for, say, internet navigation, that it might not work anymore for making calls. And so think of how reticent they are, how in being involved in trial and error procedures. Older people don't like to do that, don't like to try out things and to discover how a certain thing works. Because it's cognitively demanding. You have to remember what you did before in order to be successful in the next step. And of course, it leads you towards uncertainty. And uncertainty, when you're old, typically is something that you would like to avoid. So these are very, very common barriers that you can find all over in many studies, have been reported in many studies, that are very difficult to overcome with any technological solution, because it deals with cognition, maybe emotion. We have complex assistive technology, screen readers. They change the way people interact. They change the modality. They change the medium from a two-dimensional visual representation to a monodimensional, irreversible temporal representation. They change the output modality and the input modality, so people don't use mouse, or if they use a touchscreen, they use it in a certain way. It changed the kind of actions that people can do. The screen reader might work in different modes. So you could be scanning the page, you could be accessing tables, complex data tables, you could be accessing forms, you could be accessing lists of links, etc., etc., etc. The problem is that, well, there are two problems. You have to be proficient, you have to learn how to use proficiently this kind of technology. And if you're a developer, then you have to figure out how people would going to be using the website, using these kinds of operations and visualizations, etc. And developers tend not to have this kind of experience, especially young developers. Accessibility is also a very difficult thing to evaluate. This is a chart that has to do with an experiment we did 3 years ago. We asked more than 30 experts in web accessibility to use the WCAG success criteria, the 2.0 WCAG success criteria, and tell us on a certain fixed set of pages what they thought which criterion was failed, pass, or not applicable. And these points here show you how many in percentage of these experts agreed on a certain amount, on a certain outcome. So for example, there are success criteria that reached almost 45% of the agreement, whereas there are other criteria that went up to 100%. But if you look at this curve of the different success criteria, you'll see that many of them are below a threshold of 80%, which means that in that experiment at least, evaluating accessibility by using WCAG when done by experts is not so reliable as a procedure. It doesn't produce reproducible results. Why? Because accessibility is a complex thing. It has to do with the pedagogical aspects, it has to do with ergonomics, it has to do with user experience, because you're dealing with people and the way people interact with information in general. So what can we do? One possible way is to use to approach the development of systems in a slightly different way and use models that represent the deep aspect of a certain kind of system or user interface. For example, I'm jumping to the example so that you can understand at least in a concrete sense. Imagine an application that can be used to control the lights in a room like this. The right section of the light, the center section of the light, the left section of the light, plus the connection to the screen, turning on and off the screen, connecting the PC to the projector, and changing the ventilation level. This could be an interface for doing that. It has three sliders where you can slide the intensity of the lights. It has 3 checkboxes to turn on and off those lights. And then a set of radio buttons for changing the ventilation level from off to high level. And then a set of checkboxes and radio buttons to turn on and off the screen, the projector, and selecting the input for the projector. So what kind of models can we use for representing this kind of interface? Well, this is a UML diagram. UML is a visual language for modeling and specifying software systems. So in this model, you say what kind of data the system is going to use. In our case, what kind of data the user interface is based upon. So you're saying there will be a panel with 3 different, 1, 2, and 3 different light banks, light sections. Each section will be characterized by a level, a number, and a Boolean value, true, false, representing whether the light is turned on or off. And it has a certain number of operations. You can turn it on, you can turn something off, you can set a particular level. For the audio video, you have a similar representation of the data, saying what's the possible input and whether the screen is on and off and whether the power of the projector is on and off. And similarly for the ventilation level, you have a value here that represents off, low, medium, high ventilation level. So this is for the data, for the concepts manipulated by the user interface. For the dynamics, you could use something that was developed in the 1980s, ages ago, for modeling the dynamics of very complex reactive systems like devices on board of airplanes. And the key notions here is that you can model the behavior of a device by representing the possible states in which the device is and transitions between states. So I'm going quickly. So this will be part of the model. You can represent that the left part of the light is something like this, a big block that contains an on state, an off state, and arrows connecting, representing the transitions from on to off and vice versa. In addition, when the state is on, you can have a substate, a more specific one, and allowing you to to represent the fact that you could increase or decrease the intensity of the lights. So, in a sense, this block here represents the behavior of one section of the light. Because you have three sections, independent, one from the other, you represent, in UML state machines, you represent three of these blocks as adjacent regions, meaning concurrent region, parallel region, things that can evolve independently one from the other. You could represent the dynamics of the other part in a similar way. For the ventilation thing, you say, well, there are four possible levels of four possible states, representing the four levels, off, medium, low, and high, and transitions allowing you to switch from one to the other, and this would be one way for representing that, and for the audio-video control in a similar way. Because these sections also would evolve independently, then you could represent them as separate components again. What you can do then is, if you don't want that particular design and you want to change the way in which the system behaves, you could simply change a bit the topology of this graph, of this diagram, adding new arrows or perhaps moving the states in a different ways, and this would represent a slightly different behavior. Which one? Well, for example, this one, where you have one light in the foreground, and then you could switch to the center or to the right section. And the other part of the interaction are the same. So the data is the same. For the two screens that I showed you, the data is exactly the same. What changes is the behavior. So how does it deal? What's the conclusion here? What's the benefit for accessibility? Well, one thing that is important, I think, is that imagine that a user interface would be enriched with this deep information about what state is current and what are the possible future states and what are the actions that the user could do in a certain point in time. This information could be embedded in the user interface, and therefore the user could be given information about what is being displayed at a certain point, what actions are possible, where do these actions lead, what will be the future state, can I go back, what would be the best way to go back, and when I go back, where do I go? How many clicks do I need to reach a certain kind of functionality? Is there a shortcut? Are there alternative paths to go in that way? So think of this kind of information provided by models and compare it to the level of information that is currently available or could be made currently available in user interfaces. So I think that the kind of information that I'm thinking at is at a level that is more abstract and much deeper in terms of the semantics of the user interface. Now, I don't have a solution though. This is a direction I would like to go. Up to now, the examples I showed you were built automatically by a tool written in Java that we developed that takes as input those kind of models and produces prototypes, running prototypes of user interfaces in JavaScript, jQuery, HTML, HTML5, etc. Currently marked up with ARIA and etc. It would be interesting to see how that deep information could be embedded within the user interface and how that could be conveyed to users that might need that, like people using a screen reader. So I think that this could help somehow moving forward, that kind of plateau, that kind of level that I mentioned at the beginning. And with this, I'm done. Thank you for your attention.